Now, in a scenario where the fly is experiencing adverse vibration, those vibrations can be sensed throughout the body by different organs. In this example, we see the antenna shake. Sensory neurons that go from the antenna to the brain, called Johnston's organ neurons, respond to that vibration. They can cause the activation of, for example, this orange neuron, which is a threat response descending neuron that goes down into the ventral nerve cord and causes the antagonistic activation of motor neurons, enabling the fly to brace. At the same time, via this green neuron that goes back up to DNG 100, it inhibits DNG 100 so that the fly stops walking. Together, this is a stop and brace reaction. We've managed to demarcate larger groups of neurons through the neck that we think are causally involved in organizing many different behavior classes. We have done this with a similar logic of tracing circuits and their connections and trying to make sense of them. Here on the bottom right, we're showing a UMAP embedding of these neck neurons in connectivity space, which we've interpreted by looking at how they link up to sensory incoming information and how they lead out to motor and endocrine action. Together, this begins to paint a picture by which different sensory motor low-level modules are combined and recombined by higher-order long-range projections that themselves can interact in a system where different kinds of behavioral modules can subsume one another. This resembles an influential idea from autonomous robotics known as subsumption architecture, and we think that the nervous system of the fly is built along similar lines.